Let's continue solving Project Euler. Today, 2 hours ago, I solved this problem. So it appeared today, and it was the first time that I solved a recent problem. But our main goal is to continue grinding, as they say. So let's move on to 49th problem. So we have an arithmetic sequence in which each of the terms increases by 3,330. It is unusual in two ways, because each of these terms are prime and each of the four digits of the four-digit numbers are permutations. There are no arithmetic sequences made up of 1, 2, or 3-digit primes exhibiting this property, but there is one other 4-digit increasing sequence. Another one easy problem. Increasing, so we cannot take this backwards. So let's do it. Oh no, I did something wrong. So this is the correct naming here, and instead, what's wrong with you? And instead I needed to rename this one. Mm-hmm. 49, 49, and here I also need 49. We don't have an input. Well, okay, we can take input 4, I think. Mm-hmm. Let's go. So, since it is a number, we will use long long. We also need primes. I really would like to have some sort of library. So let's make a library, I think. So to make a library, we will start with creating probe, not probe, but like lib.hpp. It will be lib.hpp. So lib will contain. Okay, let's write like eratosines. What? You cannot rename it? Okay, let's write eratosines.hpp, and it will contain solely eratosines. I don't remember which file contained it, however. Maybe 36th? Okay, let's... oh, 37. So let's take it. And we add it here. Let's include something here. Include vector. Is it enough? Yes, it is enough. Maybe runtime error, so we would like to have std accept to use runtime error, but that's it, I think. That's it. So here we can simply include errata_things.cpp. Now we can use errata_things as usual. So let's go. Let's actually go. First of all, I would like to find 10 to the power n. So I say int power, like int ans equals 1, while b, if b and 1, a times equals b, ans. If b 1, a times equals a. And here should be a, and we return ans. Int power of 10 and n. Actually, I would like to have this function somewhere. Okay, what then? Next. Yeah, now we have errata_things. Now we would like to go through all primes. So let's go through all pairs of primes. So if p is at least n, then we push back it. Then we go through all of them. So first of all, it's I plus 1 here. So we need to check several things. First of all, we would like to check that the second number is a permutation of the first one. To do that, we simply check that. Well, no. Instead of doing that, I think we would like to find out all permutations here. So what do we do? Let's take permutations. Let's take vector int digits. Let's just primes here. Actually, we can just do it like this. We don't need these primes. So let's take this number p and store all its permutations here. So we push back digits temp %10 and temp divided by 10. So now we have all digits here. Let's sort them. Now let's go through all of their possible permutations. So what do we do? First of all, we take our digits. So we say int int ans equals 0, and for int I in digits, ans equals 10 times ans plus I. And permutations dot pushback of ans. So now we have all numbers here, and we can sort them. Fine. Next, also we only want numbers which are greater than p. Yeah, so if answer is at least, let's also keep track of, okay, fine, if answer is less or equal than, is greater than p, only then we do it. Okay, now let's sort them, and let's go through these numbers. Also, I only want prime numbers. So if c dot is prime p, only then I do it. Once. So let's go through all permutations. Now let's check. So we have number q and number p. Now we want the next number, which is 2q minus p. So we need to check that 2q minus p is also in permutations. Okay, so let's store all these triples. So we have vector ll answer. So if 2q minus p is also here, that is permutations. So let's take lower bound of permutations dot begin, permutations dot end, and this number. Do I have algorithm? I do have algorithm. Why doesn't it work? Permutation. So if it is not permutations dot end and it is 2q minus p, then we can report this number. What does it mean to report? We push to answer this triple. What is this triple? This triple is number p, then number q, then number 2q minus p. But we cannot push it one by one. We need to push it as a whole. So we need to multiply it by n, this by n, and actually p we need to multiply 2 times by n. Okay. So we have pushed it back into the answer. Okay, and finally we need to go through this array, check Can we copy it? We can't. So 1 4, if A is not 1487, 4817 and 8147, if it is not equal, then we can return it. Else we return -1. It took quite a while, unfortunately. So I hope now we will get the answer without any problems. We didn't. Ah, I get it. The problem is we didn't use... Okay, let's use namespace std before it. Why so long? It takes really long time. Ah, it's here because we forgot to divide by... So let's say that if we failed to find next permutation, let's like rewrite it as do while. Do while next permutation of permutations that begin, permutations that end. No, not permutations, but digits. Okay, now it worked, and we found the answer, which is negative. Ah, I see. This is because this should have done without the overflow. The easiest way is to write long here. Now it's simple. Ah, it's quite a nice triple. I like it. A lot of 9s. Problem 50. Prime 41 can be written as the sum of 6 consecutive primes. This is the longest sum of consecutive primes that adds to prime below 100. The longest sum of consecutive primes below 1000 that adds to a prime contains 121 terms and is equal to 953. Which prime below 1 million can be written as the sum of the most consecutive primes? Well, this time, this is even interesting. So, let me write something. So let's take all primes below 1 million. And let's sum them. So let's say that u0 is 0, u1 is p1, u2 is p1 plus p2, etc. Great. So we need to find a sum of some primes below 1. To find a sum of primes. So how do we do it? We simply say that Q let me think. We simply say that Q K sum of primes from L to R is QR minus QL minus 1. So we want it to be a prime number, and we want to maximize R minus L given that given that what? Just maximize R minus L given that it is a prime number. Given that QR minus QL minus 1 is below 1 million. So how to do it? Let's store all prefix sums here. That I can actually start writing because I understand what to do. So let's say that we take this. We again need to include eratosthenes. We need to switch to the next project. We need to switch to the next project here as well. We need to use the next input file and output file. We need to create a new input file which contains a single number 1 million. Okay. So we start with eratosthenes. And we know all these primes. Then let's find prefix sums of size c dot. Let's actually store this number k, which is simply c dot primes dot size. And we store k plus 1 sums where prefix sum of I plus 1 is prefix sums I plus c dot primes I. Nice. Then let's store our actual answer. So we need to store two things. We need to store long length, so the number of primes, which is initially 0, and the sum of them, which is also 0. And then we will return p for the maximum length. So let's go through all primes. So we start from 0, We go at most k plus plus I. Okay, let's think. So we need to take pi plus etc. plus at least p length plus I plus length. At least this number. So if I plus length, so this means that we need to take prefix sums of I plus length plus 1 minus prefix sums of I. So if it is greater than, if it is at least n, then we simply break, because we cannot increase our answer. Moreover, if this number is greater than... Okay, this can be checked here. So we can say that this... Why k actually? So this should be at most k. So we break. Otherwise, we need to iterate over all possible lengths. So for int j equals length plus 1, still we need to check that I plus j is at most k, and plus plus j. So let's look at the sum, which is prefix sums of I plus j minus prefix sums I. So if this is a prime number, so if sieve dot is prime of s, then we're happy. So first of all, if s is at least n, then we break, because this is too much. So if this number is prime, we can increase our answer. So we say that p equals s and length equals j. And that's it, we return p. Let's go. So it says that this number is the answer, let's print it. Great. Problem 51. By replacing the first digit of the two-digit number *3, it turns out that 6 of the 9 possible values are all prime. By replacing the third and the fourth digits of this number with the same digit, we have 7 primes among the 10 generated numbers. Find the smallest prime, which by replacing part of the number, not necessarily adjacent primes, with the same digit, is part of an 8 prime value family. Okay. Eight digits. So what would be the answer for this family? 13? This is not clear. Let's actually just find the smallest prime in... Let's just find the first prime in the family. So what do we need? We need to do the following. So we iterate over all possible numbers. We take a number, we iterate over possible positions, we choose some positions in this number, yeah, so we choose some positions in this number. After that, we would like to iterate over all numbers which can be got if we take these positions. Well, actually, I only want to take the positions with zeros. So let's only take positions with zeros. Okay. So we find out how many different primes are there, and we take the minimum of them. Okay, let's try actually to do it. Well, it's again a problem where we need eratosthenes. Eight. It's again a problem where we need eratosthenes. 51. 51, 51, and finally 51. So we need to find n primes with this property. So let's go actually for int I. Let's choose some size of eratosthenes. Somewhat random. Yeah, actually, yeah. Let's go through all numbers. Actually, I don't want to replace them with zero. I would like to take ones, because if I take zeros, then I have a problem. I don't have a number 0, 3, so that it can be replaced with just okay. Fine. Let's store n, which is the strict upper bound, and let's store the number of digits. . upper limit is 10 and number of digits is 1. Okay. So we go through all possible numbers. We store an errata since. So if let's actually add size here. Which is max min divisor dot size. If sieve dot size is, then I don't need this upper limit because it is simply, well, I didn't need this. So if I is at least upper limit, then unfortunately I need to update all of them. So I say that upper limit times equals 10 plus plus digits and sieve equals errata since of upper limit. Well, now we take our number. The next thing we need to do is to find all positions with ones. And we will store a binary mask of these positions. How do we do it? We simply say that so we go through all positions, starting with, okay, let's just say int temp equals I, and also we have int step, which is 0. Not really step, bits with ones, let's call it. And int current digit, which is 0. So while temp, let's do the following. Let's say, look at the last digit of temp, temp% 10. So if this digit is 1, then current digit is 1. So we need to say that bits with ones or equals this current digit. Then we need to increment current digit, temp divided by 10, and bits with ones, and plus plus. Yeah, actually that's it. Okay, now we have our mask. What I would like to do, I would like to have the vector int steps. So if I have some binary mask, for example 1101, I would like to have the decimal number, which is exactly like this, 1101. This is what I would like to have. And it is not really hard. So let's start with 1. So if I have an empty mask, then I have number 0. Let's write a function get step. So how do we find a step? We would simply like to return steps s. However, maybe steps is a short array. So we say that while steps dot size is at most s, we need to do something. We need to find step for number steps dot size. So how do we do it? Actually, it's not hard. We need to take steps of step dot size divided by 2. We need to multiply it by 10 and maybe add 1. We need to add 1 if steps dot size is an odd number. Great. So now we can get step. What next? Now we need to iterate over all possible submasks of this thing. So let's go int mask equals 0. How to iterate over all submasks? Let's think about it. So we have some mask. We have some submask. So we need to add 1. And sometimes it already works. However, sometimes it doesn't work because we had 111 here. And it became 111000. And it is unfortunate. What can we do then? We can go in decreasing order, because in decreasing order it's somewhat easier. So we have a mask, we need to subtract 1 and take AND with this supermask. So this is a supermask and M is submask. We need to subtract 1 and take AND with M. Let's actually do it in decreasing order. So let's start with bits with 1s. Mask should be positive because we are not interested in the 0 mask. If we have a 0 mask, then this means that we don't have any digits to iterate, and we simply stop. Okay, finally we need to say that mask equals mask minus 1 and bits with 1s. Well, what do we do here? First of all, we take the base, which is I minus bits I minus get step. So let's say that we have step equals get step of mask. So now we need to iterate over all digits to replace this mask with these digits. However, sometimes we cannot take 0. So let's write it like this. So we can use starting digit 1, only 1. We cannot use 0. We need to use 1. If the first digit is in mask, that means that number of digit minus 1 equals, it is in the mask, equals mask and this is greater than 0. So if this is greater than 0, this means that mask I can just write like this. Yeah. So if mask contains number of digit minus 1, then this will be 1, and I have to start with starting digit 1. Starting digit d is less than 10, and we need to check for primality. So we say that sieve dot is prime base plus d times step. So if it is prime, then plus length. And if length is at least n, we need to stop. We simply return let's also say that int min prime equals, well, like step plus base times 9 plus length, and we say that if min prime is greater than this number, then we make an assignment. So if length is at least n, we return min prime. That's the solution. Again, it took quite a lot, unfortunately. So last but not least, we replace with 51 and we run it. Let's first start with 1. Maybe it's easier. And it found 1. Yeah, because you can... because you can... But 1 is not prime. 1 is not prime. How is it possible that you replaced it? Min prime is 1, but why? Step is 1, base is 0. So for some reason it said that 1 is prime number, while it is definitely not. So I have an error here. I say that 1 is a prime number. This is unfortunate. Base plus step times d is not a prime. What? Okay. The problem is I needed to write it like this. Base plus step, not step plus base. Okay, this is easy. Now let's take 2. And still it works. For 3 it also works. For 4 it also works because 2, 3, 5, 7. But for 5 it won't work. And it doesn't work at all. I is already 1. What? Ah, I needed to write like this. Yes. Okay, now it found 11. But we don't know what we need to replace. The first digit. So the first digit. So 11, 31, 41, 61, 71, and... But it's not enough. It's not enough, is it? So 11, 31, 41, 61, 7... Ah, it's enough. Yeah, it's enough. Let's look at 6. For 6 is found 13. For 7 it found this beautiful number. And finally for 8, it finds this huge number. I think it won't work because it doesn't make... It is a part of this family, so yes, it is fine. Let's go. It can be seen that this number and this number. Unfortunately, I just know the answer. Let's go. There are exactly 10 ways of selecting 3 from 5. 3 from 5. Ah, yeah. 5 choose 3 is 10. In general, this is true. It is not until n equals 23 that a value exceeds 1 million. How many not necessarily distinct values of this are greater than 1 million? To do that, we need to calculate all these numbers. And to do that, we would simply like to use Pascal triangle. Let's use our Pascal triangle. So we need 2 numbers actually in the input. We need 1 million and we need 100. So we read n and we read the bound. Also, we need to add 52 here. Ah, it's 53. Unfortunately, I was too fast about solving 52. So we need to solve 53. So I rename this one and I put it like this here. Great. Also, I need to rename input file. And I need to rename it in the code as well. So we create a vector of int, choose of size n, and vector int of n as well, for example. Now we go through, we say that choose 1 1 is 1, 0 0 is 1. Then we go through n is from 1 to 100. Fine, let's go from 1 to 100. So what do we do? First of all, we need to calculate all these chooses in our Pascal triangle. So we take the previous row, I minus first, it has I numbers. Yeah, so actually it should be n plus 1 here. And it should be n plus 1 here, so it should be n plus 2 here. Actually, we don't need a two-dimensional array, we only need the last row. We only need the last row, which is of size 1 and contains one number. So we calculate new choose equals choose. Then we need to push back. We can actually do it in place as well. So what do? We say that choose dot pushback 0. Yeah, so we have C0, C1, etc., Ci. Now we want to have C0, C0 plus C1, C1 plus C2, C2 plus C3, etc., Ci plus Ci, Ci minus y plus Ci, and Ci. To do that, it is easy. We need to push back 0 and then add each number to the next one, like this. So we push back 0, we go through all numbers starting with the last one but last. So we start with I minus 1. J is at least 0, minus j. And we say that choose j plus equals choose j plus 1 plus equals choose j. However, this is not correct, because this might overflow. So instead, we need to say that it is minimum of this and our bound, which is b plus 1. And if this number is greater than 1 million, then we need to plus ones. Formally, this only checks this, etc., this number, but it doesn't check C0. So we at last need to say that if 1 is greater than b, then also plus ones. And return ones. Okay, let's go. Unfortunately, we have a failure. So when we have some I, choose has the size of I. After that, choose has size of I plus 1. So we can start it has a size of I plus 1. So we can take I minus 1 and take I minus 1 and I and work with them. Maybe we don't have the input file formatted correctly. No, we have it. The problem is that we have it. Oh. What? Okay, let's look in the debug. J is 0. Choose is of size 1 for some... yeah. This is a not the cleverest bug in the world. $4,075. It seems that we solved the problem correctly. It's a poker. In the card game poker, we have these combinations. I will ignore them because I know them. If two players have the same ranked cards, then the rank made up of the highest value wins. Okay. Input 0054.txt. This is sad. I don't know what does this problem do in Project Euler. I really don't get it. Well, so here we need to read a lot of poker combinations. Okay. Let's make something. So we need, let's start with structure card. Let's start with actually enum rank. I don't want it. Okay, let's just store a card as a char. So let's say that using card equals unsigned. Okay, uint 8t. Then using hand equals array card 5. and using round equals pair of hand and hand. So let's find ans one round. And let's find ans for the vector of rounds. We need to find out how many rounds are won by the first player. Let's return here 1 if the first player wins, -1 if the second one wins, and 0 if it is a draw. So if find ans one round of round equals 1, then we plus ans. And here we return ans. So now we have two separate problems. How to store everything in a vector, how to read the input actually. And how to compare two hands. Let's start with the easier thing, which is reading the input. So iStream operator greater. So let's start with reading one card. How do we do it? It's quite simple. We read two charts, which is rank and suit. Then we need to store this information in our card. So let's start with these two functions, chart to rank and chart to suit. So here it's easy, it's like a switch statement, switch R case. So we have diamonds, clubs, spades, and hearts. So let's iterate over them in any order. Case diamonds return 0, case clubs return 1, case hearts return 2, and case spades return 3. And let's work out the ranks. So if R is at least 2 and R is at most 10, is at most what? What, 10? Is at most 9. Then I return R minus 2. After that, it's quite simple. We switch R, so case t, then we need to return. So 8, case jacks, return 9, case queen, return 10, case king, return 11, and ace is 12. And here we simply say that we need to chart to rank of rank plus chart to suit of suit times 13. Then we return card, return in. Okay, now we can read a card. Let's say that if we failed to read it, we just return in immediately. So how do we read a hand? We go through all cards in this hand. And again, if we fail to read this card, we return in. Why do you fail to iterate over hands in a cards in a hand? Okay, whatever. What? What's wrong with you? I cannot iterate over an array? What? Are you nuts? No, it can't be. How can't I iterate over an array? Are you kidding me? Can I just say that, like, card 5? Ah! I maybe understand what happened. I didn't include array. Well, now it works. I just didn't include the array. Yeah, finally we need to read around. And this is the most simple function. We return in read round dot first and round dot second. Yes. So here we need to while true, while in read round dot back, rounds dot and place back. Then we round dot pop back, and we find dance the rounds. So here we need to finally find the answer for one round. And I think we will find out some way to store the result of the game in a vector. And after we have done it, it will be lexicographically bigger for the winner. So we need to return that get result of round dot first is greater than, actually no. Is it like CMP? Compare. Okay, fine. Auto first equals get result first. Second equals get result of second. Return. So if first equals second, then 0. If first is greater than second, then 1. Else, if first is less than second, then -1, else 0. Now we need to get the result. So actually I will ignore royal flush. It will be same as straight flush. There's no reason to distinguish this and this. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8. I have 9 combinations from 0 to 8. So this will be the first element. So let's start with straight flush. Actually, let me think. So we have a hand. We need to check if it is nice enough. Actually, fine. Let's also work out the royal flush if we need. Okay, let's start with the flush. So how flush is the only moment when we're interested in rank, actually. So in suit. Let's go back. So int get suit from card. So we have card. We need to get suit. It's simply a residue modulo 13. So let's go through all. Bool has flush. Let's go through all. Numbers. So we take a card. If get suit of card equals get suit of hand 0, if it does not equal, then we say that has flush is false and break, and in the beginning it is true. Okay, now it has flush. So we have two cases, if has flush or not. Let's start with this one. If we have flush, then it is either this or this or this. The next thing is actually check for straight. How do we check for straight? So we need to find all let's make a vector of size 13. We can either use rank occur of size 13. And let's initialize it with 0. So here we also increment rank occur of get rank of card. To get rank, it's also kinda easier. We need to divide by 13. No, actually this is divided by 13 and this is percent 13. So now let's check if we have a straight. How do we check that we have a straight? Let's say int straight equals 0. So let's go through all numbers. So if rank occur I is greater than I is greater than 0, then we say that we have plus plus consecutive. Else consecutive is 0. And if we found out that consecutive is 5, we say that straight is I. There is one exception, which is ace 2, 3, 4, 5. So we actually need to start with the ace. So consecutive is rank occur 12 is greater than 0. After that, we do this. So if has flush, then if we have a straight flush, then if straight equals ace, we return a royal flush, which is 9. Else we return a straight flush, 8 and straight. Else we do not have any straight and we need to compare as far as I remember, flush is compared. So if two players have the same ranked hands, then the rank made up of the highest value wins. Then highest cards in each hand are compared. So actually we need to sort all ranks. Yeah, so let's sort all ranks, I believe. So if we have a flush, we need to sort all ranks in this flush. So let's do it. Auto add high cards. So we go through all ranks, and if and for int j equals 0, j is less than rank occur I, v dot pushback I, and then we don't return anything. So here we need to ans consists of 1, 4, I believe. 0, 1, 2, 3, 4, 5. 1, 5. And we return ans. We return. We add high cards. And we return ans. Actually, let's just return this. Okay, else if straight greater than 0, it's easy to see that since we have a straight, we cannot, and we don't have a flush, it's just a straight, because flush, no full house, no 4 of a kind, and none of these ones. So simply return of 4 and straight. Okay, now we don't have a straight and we don't have a flush. This means that we can only have 4 of a kind, full house, 3, 2, 1. Okay, it's easy, so let's say that we have 4, 3, pair, second pair. So this is what we're interested in. Let's go. So if rank occur of I is at least 4, then 4 equals I. Else if rank occur is at least 3, then 3 equals I. Else if rank occur I is at least 2, then it's interesting. So if we have already have a pair, if we don't have a pair, then we say that pair equals rank occur. Else we put it into the second pair. Actually, I should be here. That's it. Then let's look through this value. So if 4 is not -1, we return 4 of a kind, which is 6, 7. Return 7, 4. And actually, we always need to add high cards just in case. So ans equals 7, 4, and we return add high cards to ans. Else if 3 is not -1, then if pair is not -1, then we say that answer equals full house on 3 and pair. Else we don't have a 3, then we simply say that answer equals 3, 3, pair. Just 3. Else if pair is not -1, else if second pair is not -1. Then ans equals 2 pairs, pair, second pair. Else if pair is not -1, then ans equals pair, else ans is 0. That's it. $376. Actually, I don't like this number, so let's check that we don't have too many draws. Usually there are no draws, actually. There were no draws. Whatever. Whatever. It forgot me? Well, it's correct. However, we spent too much time on this problem and it wasn't particularly useful for me. Okay, if we take 47, reverse and add, then this number is palindromic. It is not actually incredibly surprising. Not all numbers produce palindromes so quickly. Although no one has proved it yet, it is thought that some numbers like 196 never produce a palindrome. A number that never forms a palindrome through the reverse and add process is called a literal number. Due to theoretical nature of these numbers, and for the purpose of this problem, we shall assume that a number is literal until proven otherwise. Literal. Literal or literal? Let it be literal. In addition, you are given that for every number below 10,000, it will either become a palindrome in less than 50 iterations, or no one with all the computing power that exists has managed so far to map it to a palindrome. In fact, 10,677 is the first number to be shown to require over 50 iterations before producing a palindrome. Surprisingly, there are palindromic numbers which are themselves like real numbers. The first example is 4994. How many like real numbers are there below 10,000? So we definitely need GMP here. Okay, it's not the worst problem on earth. I don't hate it. I don't hate it because it doesn't take a lot of code. So now, for most of the problems, the bottleneck is my speed of coding, because I don't spend too much time to solve them usually. $10,000. I need the 55th file. I need to add this magic line here. And I need to switch to it here, and I need to... Did I copy some random... Yeah, I copied some random file. Okay, let's remove all this. Yeah, all of this. So 10,000, and we know that it becomes in less than 50 iterations. Let's also take this. So we need to go through all numbers from 1 to n. I need to make b minus 1 iterations. So I need to include GMP. I have CPP int, or how it's called. I already forgot. Okay, let's see here. 25. Ah, MPZ class, of course. MPZ class. MPZ class u equals n. Ah, MPZ class equals I. So I do the following. I try to take its string to reverse it and say that u plus equals MPZ class of reverse string s. Actually, let's each time. So let's do it beforehand. So I want this string beforehand. So first of all, I reversed it, I add it, and I again ask for this thing. And I need to check that it is a palindrome. Actually, let's store the reversed string. Let's store the reverse string. So we do this. We store it again in S. We also store it in T. We reverse S. And if S equals T, then we say that good equals true and break. And good is not like rel. So if it is not good, then it is a like real number and we need to increase the answer. Let's go. And we have a problem. And we again have a problem. Zero, 8. I need to, maybe I need to remove zeros from the end always. Because it seems that it, okay, let's say that base is 10, I don't know. Yeah, it helped a lot. Because when I wrote A08, it for some reason decided that it is an octal number, and an octal number cannot have an 8 in it. Okay, 249 like real numbers. A Google is a massive number, one followed by 100 zeros. This is almost unimaginably large, one followed by 200 zeros. Despite their size, the sum of their digits is 1. Consider natural numbers of the form a to the power of b. What is the maximum digital sum? It's again just a problem to check my GMPXX. Okay, let's save this. Let's write 56 here, 56 here. Finally, let's save this and let's create input 66. Here we need to put 100. So we read n, we find out ans n. What do we do here? We need to iterate over all possible a's and all possible b's And we need to find, we take MPZ class of A, power, can we, like, what is the power function here? Can we calculate powers? Okay, I don't see how can I do it, so let's do it in linear time, simply. So we have MPZ class A equals A. So here we say that, what do we do? We need to take a dot psi, a dot gets through, then we iterate over all chars in C and find sum of digits. Sum of digits plus equals C minus 0. So we also store the maximum number of digits. So we say that max sod is max sod and max sod. And also if b plus 1 is still less than n, we say that I is multiplied by a and return max sod. No, we switch to the next one. $972. It's quite a lot. It's really a lot. How is it possible? I don't believe it. So if max sod is greater than sod, I would like to look at this number. Then max sod equals sod, and please print this number for me. Ah, I get it. So yeah, it's not big. So the maximum possible sum of digits of a number with 200 digits is like 1800, and we have 2 times less. Okay, 972. I don't understand. Do people there really found something useful? Well, it makes perfect sense. This is a cheat. So how much exactly did my 5 milliseconds? It's even faster than this one, although this one... So, although GMP is fast, it is slow in terms of it has to spend a lot of time on this function of changing bases from 10 to 2 and vice versa. Also, and that's actually it. But this algorithm is actually linear. If you have a small number n, which you multiply it by, it really works really fast. So I don't see a reason why I use GMP. I only use GMP because I am too lazy to write my own long precision, arbitrary precision arithmetic, and I don't see a reason why to do it. Let's see. It's possible to show that the square root of 2 can be expressed as an infinite continued fraction. Yes, it's not very hard. The next 3 expansions are these. In the first 1000 expansions, how many fractions contain a numerator with more digits than the denominator? Actually, no, actually we can do it without GMP. We can do it purely in double. So that's what I'm going to do. So first of all, let's find out how we do all of this. So how do we find these expansions? Actually, so you have 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, etc. You think, okay, we have this thing, now we need to add 1 over 2 here. But this is the hard way. The easier way would be like this. We add 1 here, we inverse all this number, and we add 1 here. So r becomes 1 plus 1 over 1 plus r. So this is actually the way how you find square root of 2 kind of fast. It's still, there are still much faster ways, because Newton's way is like, Newton's method has the speed which is square of the speed of this method. But nonetheless, let's do it. So we have fraction a over b. Let's do all 3 things. First of all, we need to find 1 plus r, and this is a plus b over b. Then we need to inverse this, so this is b over a plus b. Finally, we need to add 1, and so we finish with a plus 2b over a plus b. So this is our fractions. And we start with something like 2 over 1. Yeah, 3 over 2. 3 over 2 is the starting one. So we need to check whether it has more digits than this one, and it is simple. We need to, if we have a fraction a over b, we need to divide a logarithm of a by logarithm of 10. And this is actually its ceiling No, it's floor plus 1 is number of digits. Actually, that's it. So we're kind of sure that this number never gets too close to a power of 10, so it's quite exact. Well, so we have an input which consists of just a number 1000. Here we go. So we start. Actually, let's start with even the previous one, which is simply 1. So int a equals 1, b equals 1, and we do 1000 iterations. So we say that a plus equals b, swap ab, and a plus equals b. After that, we need to check, is it true that floor of log a divided by log 10 is greater than floor of log b divided by log 10, then plus %. And that's it, we return out. $64. I believe 64. Let's actually sear this because I don't like it. 64 sounds like 2. 64 among 1000. Okay, 64 among 1000 is... I can believe in it. Let's still print 1, else print 0. I would like to look at it. 0, 0. So the 8 expansion is 1, yeah. Let's remove all debug output. And print the answer of 64. And go on. Sorry, but the answer you gave appears to be incorrect. What? Because I cannot use int, unfortunately. I cannot use int here. I have to use double. Or even long double. Just, okay, let's try double and long double and compare the answers. On Visual Studio there is no long double, so we only have double. So now it says 123. Let's believe it. Ah. 183 is also incorrect. Maybe it's because it is infinity in the end. I see. Okay, actually it's not very hard to fix. We need to divide them by 10. So if A, if b is greater than 10, while b is greater than 10, a is divided by 10 and b is divided by 10. Now we don't have such problem. We don't have such problem. So we simply find our nice answer, which is now 153. So we should get a well-deserved OK and go on. We will solve 3 more problems and then stop. Starting with 1 and spiraling anti-clockwise in the following way, a square spiral with size length 7 is formed. It is interesting to note that the odd numbers lie along the bottom right diagonal. But what is more interesting is that 8 out of the 13 primes lying along both diagonals are prime. That is, a ratio is 62%. If one complete new layer is wrapped around the spiral above, a square spiral with side length 9 will be formed. If this process is continued, what is the side length of the square spiral for which the ratio of primes along both diagonals first falls below 10%? Along both diagonals? Why both? Ah, both, it means... Yeah, I see what both means. Okay, let's go. So first we'll again need our Eratosthenes here. And we need to find formulae for these spirals. I have already written them in the past, but I need to do it again. So I think we need to write like the number of percents, so it's like double. And here we print 0.1, 10%. 58 here, 58 here, and we need 2 more things, which is 58 here and 58 here. Well done. So what is the side length of the square spiral? Okay, let's start with 1 by 1. So in 1 by 1 we have int side equals 1 and int primes equals 0. So let's go infinitely, and we say that side plus equals 2. Okay. Okay, let's think what comes next. Let's think what comes next. So we have a square spiral. It looks like this. This number, then this 8, then these 16 numbers, and so on. Okay, let's go. So first of all, we need to find this number. Okay, let's draw it somehow. So we have this thing, so we need to find this number. This number is actually the area of the square plus side plus o. Okay, this is the new side. Let's talk in terms of new side. So this is a new side. So we need to add side minus 1. We need to add. Actually, they are always not prime because they are all squares. So let's ignore them. Okay, so this number is ignored. Instead, we add here, and here we add side minus 1 times 2. Yeah, because we add this number, which is side minus 1, and we add these numbers, which are also side minus 1. So side minus 1 over 2 times 2. And plus side. Okay, fine. Let's talk in terms of the old side. Okay, the old side. So if we talk in terms of the old side, then we had side squared plus no, new side, of course. New side, of course. So we had side minus 2 squared plus this number. This is simply side squared minus 2 side plus 2. No, what? Actually, I'm not correct about the order, so actually it works like this. It's counterclockwise. So let's redraw it. So this is 5 by 5 spiral. And this is old side, and this is new side. Okay, in terms of no, I messed up again. So we have a square and it ends here actually. So let's go. First of all, this part, and this is side squared minus 4 side. Actually, let's use s. S squared minus 4s plus 4, this is this area. Now we add s minus 1, which is s squared minus 3s plus 3. So s squared minus 3s plus 3. So if no, let's write a function is prime. And it works in the following way. So if n is less than sieve dot size, then return sieve dot is prime of n. Otherwise, if n is at least sieve dot size, then before that we replace sieve equals eratosthenes of maximum of n plus 1 and 2 times sieve dot size. So if is prime of this number, okay, if is prime of this number, then plus primes. If is prime of the same thing with 2's, then also plus primes. What next? Then we need the third one. So here, and then here. And now it is side times side minus 1 plus 1. So it's a triangular number plus 1. No, not triangular, but 2 times triangular plus 1. 3, like 10, 21. Yeah. And finally, the square is ignored. Okay, now we check, is it true that if primes, if side, so we have, how many numbers do we have? We have side times 2 minus 1. Let's multiply it by n. So if this is greater than actual number of primes, let's print what ratio we have now instead of n. And return side. Are you kidding me? Wait, what? For some reason it exploded. Why did it explode? It is really huge. So my eretosines takes a lot of time. And a lot of memory. It is already more than 1 gigabytes. This is because using of eretosines is not the best way to check such big numbers. So let's not use it eretosines. Instead we will use a regular square root method. So if n is at most 3, returns n at least 2. And let's go through all numbers from 2 to n. So if n% equals 0, return false, return true. There is no need to use it here, so let's make it a regular function. Now it doesn't take a lot of space and doesn't take a lot of time actually. Well, it takes a lot of time. But so it took 12.5 seconds. I think we can remove all of this. We can remove all of this. And it will work in under 10 seconds. Because we didn't make so much. What? So it took a lot of time simply because I printed a lot. No way. It's what? So again, if I add this short line, it becomes 12 seconds. And if I don't add it, it works in less than a second. Okay. Well, 2 more problems, and I'm done. XOR decryption. Each character on computer is assigned a unique code and the preferred standard is ASCII. For example, this is a modern encryption method is to take a text file, convert its bytes to ASCII, then XOR each byte with a given value taken from a secret key. The plain text must contain common English words. How am I still supposed to do it, however? Mm. Well, I don't like this problem. There is no way I could like this problem. Fine, let's start with decoding it. So here here I read the string. Here I don't need it at all now. Let's use 59 here, 59 here, and 59 here. So let's start with transforming a string into a vector of numbers. So let's say that we have a vector int v. Does it end with a comma? No, it doesn't. So let's take char c for char c in s. So if c is comma, then it means that we will have one more number. So we need to replace back. Otherwise, we need to say that v dot back equals v dot back times 10 plus c minus 0, and we return v. And we start with decoding it. Into v. So now we have a vector of ints. And we need to decode it. So since it has English words, it means that there are not many options actually. It must contain common English words. Let's now try with assuming that there are only English words, nothing else, no spaces, no carriage returns, nothing like this. So let's make it string, I think. Okay, whatever. Yeah, so let's say that we have a string key of size 3. Actually, let's do it separately. Let's do it separately. So let's just go through I equals 0, I less than 3, or in j equals 0, j less than 256 plus j. So let's go through all chars. So here we go through all k starting with I, k is less than s dot size, and k plus equals j, and plus equals 3. So we do the following. We say that we take s, k, we convert it to uint 8t, we convert this after that into an int, we XOR it with j, and say that it is a new char. And we store if this key is good. If new char is at least a and less than a, and at the most z. And if it is not true, let's say that good equals false now. And if good, then v I dot pushback j. And after that, let's print, let's like return 0 for now. But before that, cr v0 dot size, v1 dot size, and v2 dot size. Zero, zero, zero. Okay. Let's allow space. 2 to 2 now. Well, this is much better because it means that these are words separated by spaces. Let's now assume that the first letter should be a capital. So this means that actually, let's just write these both. Okay, let's try the following. I want the first letter to be capital. So let's write like this. So if j equals 0, no, if not j equals 0, if k equals I, then if if k equals I, then if I equals 0 and so if I equals 0, then we don't want it to be a small letter. But if I is greater than 0, then we don't want it to be a capital letter. Now it's 202. This means that it was like, it seems that it was an article. So it was a something. Let's just look at all the examples. So for int l equals 0, l less than s dot size plus plus l. Again, we take this. Instead of, actually, I want to take int u equals ijk, and here I XOR with u l%3. Then I go back to chars, and I want to print it. No. This happened because I needed to use L here. Okay, this is what we need. So for some reason we need to say that it is so for some reason it means that we need to take v0 0, v0 first, v1 0, v2 0. Then we get a text which makes sense. Yeah, do we? Yeah, we do get a text which makes sense. Let's call it code. And we need to find the sum of all ASCII values. So ans plus equals code, and we return ans. Yeah, we knew something new about Euler. Finally, problem 60. Find the lowest sum for a set of 5 primes for which any 2 primes concatenate to produce another prime. Well, it is also a problem which requires errata since, so I'm kinda glad that we used, we wrote a library. Include errata since, so the input is 5. $60. Input is 5 here. It is removed. It is removed. Here we add 60. And here we add 60. I close it because I'm tired and this is the last problem that I will solve today. So we start with a sieve. We start with a sieve. So, okay. Let's do it iteratively. So let's say that we want to find s equals like 1. While true, so we will try to find the minimum answer. For this problem. And if in the end it was the case that s equals the initial answer, if it is less than the initial answer, then we return s. That's it. Okay. Otherwise, we have to multiply it by 2. What do we do inside this function? We create a recursive sieve of size initial s. Then we need to iterate over all fives of numbers. How do we do it? I think we simply can... No, I don't like what I just thought of. Okay, let's make a recursive function, that's it. So... So what? So optimize... So let's say that we have a vector of ints. And find ans recursively given this v, sieve, and s. I think we don't need anything else. And n, of course. Okay. So, let's start with the easiest thing. Actually, so s will be the remaining sum. S will be the remaining sum. So, okay, if like if v dot size equals n, we simply return because no, maybe we need to update the answer. Actually, instead of this, we should take this. So we need to find the lowest sum of a good set of primes. So if we are here, we already have a good set of primes. Let's say like we have current sum. So we put it here. Okay, so if v dot size equals n, then S equals current sum. But also if current sum is at least S, then we return, because we don't want to be here. Actually, it will never happen. Now what do we need to do? We need to push back a 0, and then we need to pop back from V. Now let's take all primes. So V will be the set of all our primes in decreasing order. Sieve dot primes. Okay, it will be the set of primes in decreasing order. So first things first, we have our array V. Yeah, it is V. And we added a prime P. So first of all, if it needs to be less than the previous number. So if v dot size is at least 2 and v dot back is greater or equal to v dot or begin 1, then actually break, because it doesn't make sense. No. P here, it should be P here. Okay, now we need to check whether it's possible to again, if this sum is already greater than sum or equal, then we don't need to go here. Yeah, so if let's find int new sum equals current sum plus p, and if new sum is already at least s, then we also break. The next thing is to check whether it's true that all pairwise concatenations are prime. And we can do it in, actually we can do it in square root of n time. So let's write a function is prime. Again, it can be done here. Actually, let's also pass eretosines. And if n is less than sieve.size, return sieve dot is prime of n. Otherwise, let's do it the usual way. So if n is at most 3, return n is at least 2. For int I equals 2, I times I is at most n plus plus I. If n% I is 0, return false, return true. And here, so we need to make all possible concatenations. Let's start with power of tens. We will need them. Power of 10, const int n. Static vector int answer if n is 1 actually. So while n is at least ans.size, ans.pushback, ans.back times 10, and return answer n. So this is power of 10 function. Yes. So we need to iterate over all numbers in this array V. So if good, and then we say that v.back actually we always say that v.back is p, but if good, then we will go into this recursion. V sieve current sum plus new sum Sn. Find answer recursively, and that's it. So const int s equals v.size minus 1, and we need to check it for all numbers till s. So we need to concatenate vi and p, and then p and vi. So if not is prime of this, then good equals false. Break. And if p and vi is not prime, then also break. Now let's write a function which concatenates two numbers. Here we need to simply multiply it by length of p and add p. And here we need to multiply p, actually power of 10 of length p minus 1. And here we need to multiply p by power of 10 in vi plus vi. So we need to write a function length. It is easier, it is simply toString of n dot size. Finally, we have done it. So fast. 1. Nice. I don't believe it. I don't believe it. Or do I? Okay, let's try. It would be nice to look at these primes beforehand. Yeah, it would be nice to look at them beforehand. Okay, let's then do the following. Let's say that let's see. So this is the set of that primes. I need to find the lowest sum. So what's wrong? So it is the lowest. Okay, let's start with 4, for example. $305. Maybe I failed to concatenate them. Yeah, maybe I failed to concatenate them because I need to multiply. I didn't need to subtract 1, I think. Yeah, I didn't need to subtract 1. Well, now we see this number 792. Yeah, it was incorrect to subtract 1. Now it has hard time looking for these primes. So this will take a while, won't it? Let's then write no answer below this. It really takes a while. However, okay, let's try to do like this. Maybe it speeds up checking the primality. Yeah, it sped up checking for primality, but now maybe it takes a lot of time to create these huge Eratosthenes sieves. Maybe 5 will be fine. Okay, I see. Let's just take one big sieve of size 50 million. Yeah, this time I don't like my solution because it takes really a long time to work out. It already passed 1 minute. Okay, what do they say? Ah, no. Okay, so I spent 2 minutes on this problem. Well, doesn't matter. Still, the problem is solved, so I'm quite happy with that. Okay, thank you for watching.